Alright, we've got work and kinetic energy. So the work equation is work is the change in energy. It's equal to force times distance times the cosine theta if we're acting at an angle to the horizontal. And kinetic energy is equal to 1/2 the mass times the velocity squared. Don't forget to square it. So we're going to calculate the work done by the following examples. A locomotive exerts a constant forward force of 5.4 times 10 to the 4th newtons while pulling a train at a speed of 20 meters per second for 1 hour. I've got time and velocity here. You might be tempted to go here, but actually the trick to this is you've got to use the velocity equals displacement over time to figure out how far it moved, because in order to use this work equation here, I've got to know how far it went. So I'm going to say the velocity is 20 meters per second. I've got to convert 1 hour into seconds. That's 3,600. I solve for the distance. The distance it moved was 72,000 meters, or 72 kilometers, but I need it in meters. Okay, so now I'm going to go ahead and use this one here. So the force is 5.4 times 10 to the 4th newtons. The distance is right here. It's 72,000 meters. And since I'm pulling at a horizontal, I can say cosine 0, or quite frankly, if it's me, I would just use a simplified form of this. Work equals force times distance. And I only use this if I feel it's necessary, if I'm pulling it at an angle. So anyway, but when I do that, I'll get 3.9 times 10 to the 9th joules. It takes a lot of energy, doesn't it? Second one, a horse is pulling a canal boat with a rope that makes an angle of 15 degrees with a canal. The tension on the rope is 500 newtons. The canal is 120 meters long. So I'm going to use this form of the work equation since I'm working at an angle. I have a force of 500 newtons. The distance is 120 meters. And the cosine of the angle will be the cosine of 15 degrees. Just dump it into the equation, and what you get is 58,000 joules. Now, careful with this next one. A 35-kilogram child climbs a set of stairs that's 5 meters high. This is, I'm doing work against gravity here. This is not, I'm not gaining kinetic energy horizontally, but rather I'm gaining gravitational potential energy. So remember that the gravitational potential energy is equal to mgh. Not a bad equation to just have in your tool chest. So in that case, I'm going to say, well, mg is 350 since it's a 35-kilogram child, and we'll assume that g is 10. That gives us a weight. The child weighs 350 newtons, and the child is climbing 5 meters high, so we're lifting him 5 meters in the air. That gives us 1,750 newtons of gravitational potential energy. Now let's look at this next one. These are easy ones to get wrong, and so therefore they're probably going to ask you this. I have a 12-kilogram suitcase. It's carried a horizontal distance of 12 meters at a constant velocity. So what you'll notice is, which direction does it weigh? So this 12-gram suitcase, if has an mg of 120 newtons this way. Now what happens is, the force acting on it, so the force I'm applying to it is in an upward direction that's equal to 120 newtons. I'm not moving it in a vertical direction. The direction I'm moving it is horizontal to the force I'm applying. I'm applying this much force, and I'm moving it perpendicular to that. And as a consequence, I'm not going to be doing any work on it. So if you want, you could say basically if I use this equation here, I would have to say the angle I'm making is 90 degrees, and the cosine of 90 is 0. So I'm not doing any work on it. An easier, more intuitive way is to say, wait a second, if you're lifting it up but you're not moving it up, you're not giving it any energy. And since I'm moving at a constant velocity, it's not gaining any kinetic energy. So the answer, 0 joules. Diagram above depicts a force F that's acting on a 34-kilogram box. The coefficient of static friction is 0.25. The coefficient of kinetic friction is 0.1. So if I want to find the minimum amount of force needed to do work on the box, what I'm going to do is I'm going to say, well, I've got 340 newtons of weight, which means my normal force is 340 newtons. And 340 newtons times my coefficient of static friction was 0.25. So 340 times 0.25 gives me 85 newtons. So I have 85 newtons is the minimum amount of force I have to apply in order to set this object in motion. But the moment it goes into motion, I don't care about this anymore. That becomes irrelevant, and what matters is this here, because now it's sliding. Sometimes instead of calling this kinetic friction, some people call it sliding friction, which is not a bad way of thinking of it. Okay, that's supposed to be sliding, not sliding. Okay, now if force F is 100 newtons, all right, well, 100 newtons is more than the requisite 85, so it will go into motion. Now what I have to do is I have to figure out, well, how much opposing forces are going to be from friction, and I'm going to say the force of friction equals mu times the normal force, which is 340. Mu in this case is 0.1 times 340 gives me 34 newtons of opposing force. So if I'm going to use the work equation, work equals force times distance, I have to know how much work is actually being done to put energy into this object. So at least in terms of kinetic energy. So I'm going to say I'm applying 100 newtons of force, and I have 34 newtons of opposing force. Gives me a net force, a sum of force, that's 66 newtons in the direction of my efforts. So work equals force times distance. The force I'm going to use is 66 newtons, because that's what's going to cause it to gain velocity. I apply that force for 3 meters. I will transfer 198 joules of kinetic energy to that box. So since it's gained that much kinetic energy, now I want to figure out how fast. Fast is velocity. So I'm going to say K equals 1/2 mv squared. The kinetic energy I'm going to use is the work done on the box. So this is sometimes called the work energy equivalence theorem. So the amount of work I did is converted into energy, and since I'm pushing it horizontally, it's not gaining potential energy, it's gaining kinetic energy, equals half of its mass times velocity squared, and when I solve that for V, what I'll find is it's going 3.4 meters per second. Alright, now I've got a 24 kilogram crate, and now I'm applying 128 newtons at an angle of 50 degrees. How much work will be done in moving the crate horizontally? This is 12 meters to the right. So in this case, I'm just going to use this form of the equation right here. I'm going to say work equals force times distance cosine theta. Force is 120. The distance is 12. And cosine 50. I can do this because it's a frictionless floor, and what I get is 926 joules. In which case, if I want to know how fast is velocity, so I'll take the joules and replace that for the K in the kinetic energy equation, equals half the mass times velocity squared, and when I solve for velocity, which is basically going to be the square root of 926 divided by half of 24, which is 12, I get 8.8 meters per second. But now what I'm going to do is, man, once you introduce friction, it just changes everything, don't it? Okay, so here's what happens. Now, this case, we're going to say the diagram above this crate here experiences a coefficient of static friction of 0.25 and a coefficient of kinetic friction of 0.2. And the question I ask is, how much work will be done in moving the crate a distance of 12 meters to the right? Well, first of all, I got to see if I can. So if I apply 120 newtons, now let's think about this. Remember, if I'm applying a force at an angle, that's going to change the normal force. So the first thing I did is I took this 120 newtons and I used the sine and cosine to resolve it into its two components. The vertical component I got by taking 120 times the sine of 50 degrees. That gave me a vertical component of 92 newtons. Now 92 newtons is the vertical component of this force, so that takes 92 newtons off of the box, so the normal force, instead of being 240, is 148. So if I say 148 times the static friction mu, I see that I need a minimum of 37 newtons to set the box in motion. Once it's in motion, I'll take that same value of 148 newtons of normal force and multiply it by the coefficient of sliding friction or kinetic friction, and I'll see to keep it moving I need a minimum of 29.6 newtons. 37 to get it going, but as soon as it's going, really all I need is 29.6 to keep it moving. Well, there's no problem because the horizontal component of this 120, so if I say 120 times the cosine of 50, I get 77 newtons, which is definitely bigger than 37 and more than enough to set it in motion. Since it's moving this way, the coefficient, the kinetic friction is going to operate in the opposite direction. So I have a pseudo FBD here because I did include the components of this force. So the first thing I need to do is I have to figure out what is the sum of the forces acting on the box. So the sum of the forces in the horizontal direction, I have 77 newtons is the horizontal component of this 120 that I got by multiplying by the cosine of 50. And I have to take away the force acting in the opposite direction, which is friction, which gives me 47.4 newtons. Is the amount of force that's actually being used to cause this box to gain kinetic energy. So now I'm going to use the work equation, work equals force times distance. The force I'm going to use is the sum of the horizontal forces, which is 47.4, times the distance I'm moving is 12 meters, and that gives me 568.8 joules. And then we go back to how fast is it going. So I just take this 568, I put it for K in the kinetic energy equation, take half the mass, solve for velocity, and I've got 6.9 meters per second, which makes sense when without friction it was 8.8. So I know I must have done it right.